Welcome to Chapter 24. Chapter 24 is very short. It's not broken up into sections. This is all of it. In Chapter 24, we're going to introduce electromagnetic waves. And the first thing we're going to do is we're going to contrast electromagnetic waves with the sound waves we just finished studying. So there is a YouTube video here, which I will let you watch on your own time. Let me describe what it shows. You have a teacher, probably a high school teacher, and a couple of his students. In front of the camera, there is a bell jar. Inside the bell jar is a cell phone. One of the students calls the cell phone, and you can hear it ring, and you can see it light up when it rings. They then turn on a pump, pull all the air out of the bell jar, and call the cell phone in the bell jar again. At this time, you can see the phone light up, that it is ringing, but you cannot hear the ringtone. Okay. They then put air back into the bell jar, call the cell phone in the jar one more time, and you can again hear it ring and see it light up. Okay. This is illustrating the difference between a sound wave and a light wave. Sound waves are a mechanical wave, and because they're a mechanical wave, they require a medium. As we saw last time, last unit, sound waves are also longitudinal. Light waves, on the other hand, are a form of an electromagnetic wave, and electromagnetic waves do not require a medium. In that YouTube video, there were actually two different electromagnetic waves at play. One was the visible portion. You saw the phone light up. The second one was an invisible an electromagnetic wave outside the visible portion of the spectrum that is actually what the signal that caused the phone to ring. Electromagnetic waves are transverse waves as opposed to longitudinal. So the thing you should be asking here is, okay, well, no medium, what's oscillating? And it turns out the thing that is oscillating for an electromagnetic wave is the electric and magnetic fields. This is an artistic depiction of the oscillation of the electric and magnetic fields. Regrettably, it's a three-dimensional phenomena that they're trying to put on a two-dimensional space. So what you have here is the electric field is oscillating up and down, so towards the top of the page and towards the bottom of the page. The magnetic field is oscillating in and out of the page at the same time, and the entire wave is moving to the right. Okay. There's lots of portions of the electromagnetic spectrum, if you will. We're going to start at the red end. So that's down here. This would be the red end of it, right? In the red end, we have radio waves. We have things like TV and phones and microwaves. Then we come into the infrared. Notice as we move forward, the wavelengths are getting smaller and the frequencies are getting bigger. We then hit the red end of the visible portion of the spectrum. This particular graph shows the boundary for the red end at 750 nanometers, which is a frequency of 4 times 10 to the 14th hertz. And then we move from red to purple or violet, ending at 400 nanometers and 7.5 times 10 to the 14 hertz. Depending on who you talk to, different physicists may bound the visible portion of the spectrum differently. Some say 400 to 750, some might say 400 to 800. I can tell you from my experience working in an optics lab that I can see wavelengths beyond 800 nanometers. I will also tell you that after a certain point, all of the light looks red. I lose the ability to discern different gradations in color, if you will. Also for reference, I will point out that there is a beautiful green laser at 532 nanometers. If you have a green laser pointer, that's most likely what that one is. And then there's a beautiful red laser at 633 nanometers. This is not a red laser pointer. Red laser pointers are off of laser diodes and are probably closer to 700. Okay, so leaving the visible portion of the spectrum behind, we then go to the UV and X-rays and gamma rays, and the further onto the blue end of the spectrum we go, we end up at shorter wavelengths and higher frequencies. So because light is a wave, it has a speed associated with it. This is the speed of light in a vacuum. As we'll see in the next unit, if light or an electromagnetic wave enters a medium that is not a vacuum, then the speed decreases, but that's for the next unit, not for this one. So here is the speed of light in vacuum. And because it is a wave, we have a relationship between the speed, the wavelength, and the frequency. It is the same one we've used for a couple of units now. So V equals lambda F. In this case, we're looking at a light wave in vacuum, so that V becomes C. Okay. We can think about this. The speed of light in vacuum is 3 times 10 to the 8 meters per second. In air, the speed will be a little bit less, but for all intents and purposes, it's still 3 times 10 to the 8 meters per second. We can pick on one of our local radio stations at 97.5 megahertz. And remember, mega stands for times 10 to the 6th hertz. Given this information, we can calculate the wavelength of this radio station. So C equals lambda F, which means the wavelength, lambda, is the speed divided by the frequency, or 3 times 10 to the 8th meters per second, divided by 97.5 times 10 to the 6th hertz. And when you punch that into your calculator, that gives you an answer that is approximately 3 meters. Okay, this concludes this unit. Next unit, we're going to begin geometric optics, and we'll use some of what we've done here as a basis for that discussion.